Hello there everyone. Welcome to this introduction to PicoScope video with myself, John Parker. I'm the Distribution Sales Manager for Pico here in the UK, and I'm joined by my colleague Phil.
Nice to be here, John.
And he's one of our automotive application specialists. So in this presentation, we're going to take you through some of the theory, and then Phil's going to show you how you would connect and work on vehicle to capture PicoScope waveforms. Okay, let's carry on with the presentation. So this introduction to PicoScope video, we're going to take you through basically what is PicoScope, how we connect to components, how we capture a waveform, and of course, most importantly, how we start to understand them. So there's a list there in terms of what we're going to go through. But here we are with what is PicoScope. Very simply, it's a diagnostic oscilloscope that we connect to our laptop, and we use the power of that PC to drive the software, which in turn gives us everything that we need to look at and analyze the waveforms. Our waveform is simply voltage against time. Before we get to that, in terms of trying to understand what a diagnostic oscilloscope is, we can connect to any component on a vehicle, so anything with a wire, we would say, we pass it through that interface box. So this is the latest model PicoScope, so that's our 4425A model, and we turn that into our waveform. So that's what we're looking out for today, and a lot of what we'll be doing is looking at waveforms and starting to give you the information and understanding to look at them and see what's going on within that component. So like we say, we can look at that component operating in real time. So basically it gives us a way to view the electrical signals, the pulses if you like, through the wiring, and turn them into a waveform. So there's our waveform, and that is very simply voltage against time. So that's our multimeter there, and that's how Phil's going to start us today, plotted against time. And we plot this signal 400 million samples a second, so really, really quick speed, and that's how we can see so much detail within the waveform. So we can look at three main types of signals. Electronic signals, so things like sensors, actuators, right the way to communication networks, and of course increasingly also looking at signals surrounding electric vehicles. Then we have air and fluid pressures, so any pressure within a vehicle we can also plot against time. And then finally on to NVH, so noise, vibrations, harshness signals. Not something that we cover today in this session, but we will be doing a session on NVH shortly and in the future. So let's have a quick look, an example. So this is our diagnostic journey.
A customer arrives with an engine running issue. Just like all forms of mechanical diagnostics, the first step is to ask the customer about the problem. This is often, but not always, accompanied by a dashboard warning light. Your next port of call will generally be to attach a serial diagnostic tool to the vehicle. In our example, this gave the fault codes P0016 crankshaft position, camshaft position correlation bank 1 sensor A. With a degree of knowledge, we might assume that the most likely cause of these codes would be a faulty camshaft sensor. The technician replaced the camshaft sensor. The fault code erased, and the vehicle returned to the owner. After finding the trouble code, the PicoScope technician decided to confirm the problem with the camshaft sensor by looking at the waveform it produced. After connecting the PicoScope to the camshaft sensor and starting the engine, the PicoScope technician saw that the waveform being produced by the sensor matched the example from the waveform library. Investigating further, the PicoScope technician adjusted the wiring harness and found that the waveform was disrupted by moving the wires. After repairing the wires and retesting the sensor output, the fault code was cleared and the vehicle was returned to the customer. 2 days later, the technician's customer returned to the service department with the check engine light on again with the same fault code as before. This time, the technician successfully diagnosed the problem using the PicoScope and returned the vehicle to the customer again.
So that was our diagnostic journey. But how does PicoScope help? Well, actually, as we've seen there in that short animation, we're connecting to the actual vehicle component. So we're not looking at a signal filtered through an ECU. And we're, like I said earlier, we're capturing at 400 million samples a second. And that allows us, if we just take here, this is a typical example of what we would see in a serial diagnostic tool. So this is live data, and sometimes people get confused the difference between live data and what we see with PicoScope. So live data is often just a filter for an ECU. This is an accelerator pedal, so we're seeing both tracks there. And if we look at the same signal from the same vehicle at the same time, look how much more detail we can see with PicoScope. So we've got both tracks, but we see how they react against each other in real time. You see in the live data signal above, actually, you can't really see the detail, whereas with Pico, if you look, you can zoom in and see every single detail of what's going on. Okay, so where to start? Well, if you're new to Pico and you haven't done so yet, you can go onto our website, so that's www.picoauto.com, and you can download our software for free. So there's no monthly subscriptions or fees. You literally can download it and use it in demo mode right away now. And you can start to build up your own experience of working with an oscilloscope. So we're now working on our latest model, PicoScope 7 software. For anybody familiar with the previous PicoScope 6 software or even other oscilloscope softwares out in the market, what you will see is we have a much clearer, more compact design. And it really is designed with the user in mind. So it's a much simplified menu structure. And also it just makes it so much easier to work on with tablets, where of course we're using touchscreen. So it's a brand new user interface and experience. And I think you'll see as we go through the presentation today, just how much easier it is to work with PicoScope 7 against other similar software. So rather than me go on about it, what I'm going to do now is I'm going to flip to my other screen, and I'm actually going to show you how you would download the software and run through the basic commands and menus working on a demo signal. So just switch to the other screen if we can, Ben. So just, yeah, easy. I'm sharing my screen now, so hopefully you can see what I see. So in terms of downloading the software, I have come, I know I keep saying it is PicoAuto.com, so just be careful. Don't put PicoScope in and go to Picotech. It's the wrong software for automotive oscilloscope. So PicoAuto.com. This is the landing page, or the first page we come to. So very simple for the software. Go to downloads and you will see that we have a few options here. We have a stable PicoScope 7. We've also got the app that we'll go to. We've also got an early access version, plus there's milliohm software, so on and so forth. But for now, I would always recommend, particularly when you're starting, stick to the stable release, because that is the one that is not going to have any glitches, and it is a stable version ready to go. So in this case, obviously of recording, the last stable version was March 14th, 2024. Probably by the time you watch this, that will change, because it does change quite often. And we have versions here for Windows and also for Mac, for those of you who that might be useful. I'm not going to, you don't need to watch me download it, but you know that you just follow the instructions on screen. Once downloaded, you will get actually two icons appear. First one is PicoScope 7 Automotive, which is what we're going to be concentrating on with this video. But I'm going to come later on, as you'll see, there is a video around Pico Diagnostics. But anyway, so let's click on PicoScope 7 Automotive, and that should load up quickly. Okay, so you'll notice first of all we have what available devices they are. Now I don't have PicoScope connected at the moment, but if I wanted to, you would see it on the screen, and we will come back to that in a minute because I'm going to have a look at the reference waveform library. But this first bit, if you're watching this video, it would be very easy for you to download the video and actually follow along with everything I'm going to do now, because this demo is available to everyone, so you don't need PicoScope connected, so you can try this before you purchase the product. So we're going into demo mode, and this gives us a couple of things. First of all, we come into the guided tests. I know I've spoken about the guided tests a little bit, so we're going to have a look at them first, but also you'll notice behind it's actually giving us a demo signal. So effectively that's just a signal that we can play around with and start to get used to the features and functionality of Pico. And everything I do in this video, apart from the very last thing, just having a quick look at the waveform library, it's all going to be done with a demo signal. So everything here you can look at without having PicoScope connected. And as you can see, it's asking me to connect the device, but not just yet. So let's start with our guided test, because it absolutely is the right place for you to start at. So as you'll see, there are various things in the guided test. We've got tests for our charging and starting circuits, for sensors, for actuators, ignition systems, communication networks we're going to get to later on. Systems tests, so that's testing more than one component at a time. You'll see that. I'm going to do a quick video on cam and crank measurements later on. Then we've got our pressure transducer measurements, and of course increasingly so tests specifically for electric vehicles. And then finally we've got heavy duty and off highway guided tests. So just to keep it simple, because one of the first ones that Phil's going to do today is a camshaft sensor, so we're just going to do that. But as you can see, I've just clicked on sensors, and we've got all of these guided tests to help you connect and understand signals from all of these different sensors you're going to find across the vehicles. But we're just going to stick to camshaft position. What you will find when you choose there are different types. Obviously, if you've got technical data, that will help you understand the right test to pick. But if you're unsure, I would generally say just pick the one at the top and take your measurement. And if the signal looks different, then you can obviously open a different guided test to help you diagnose the fault. So we're going to have a look at Hall effect. That's the most common of camshaft position detection. Now we've got a choice, and we can open the guide or just the settings. Now effectively the guide is going to talk us through everything, how we connect, so on and so forth, and the settings will just set up the scope screen or the software itself, so the voltage and time-based settings plus which probe you should have connected. It will set them up all for you, but for now we're going to have a look at the guide. And as you'll see in the background, we've now opened up the so here we are. So this is our camshaft position tester, and it talks you through how we connect to the scope. So you'll remember you'll come to the point where we'll start to talk about connect, run and read. So this is our connect phase. So it shows you, how many channels of the scope you need to use to connect what accessories. So this is a single test lead and a backpinning probe, and it explains to you how you need the vehicle running. So in this case it is just engine running on idle to capture your data. So once you've done that, you should see a waveform that looks something like this. And if I just move this out very quick, you'll see our example waveform is already on the screen, ready to do that. And this gives you, so that's what we expect the waveform to look like, something like that. And then there's some notes. So the notes are around the waveform, so what shape it is and why it's the shape that it is. This is a relatively easy square edge waveform. But as you'll see when you get into, say, ignition waveforms, they're a little bit more complex. But again, it'll talk you through in the guided test exactly what's happening in each part of the waveform. Then we've got waveform library, so we can a little bit later on have a look in the waveform library for camshaft measurements. And then you've got further guidance. And further guidance is effectively, what what that component does, how it operates, why the waveform's the shape that it is, and what to look out for if things go wrong. And you'll see the symptoms here, and then what sort of failures to look out for. And then finally, you've got this really useful section, which is related diagnostic trouble codes for the component that we're looking at. So that is really, really quick run through on guided tests, and they are there to help you. To get back to the beginning, you just work your way back and away we go. So yeah, like I said, we've got 9 sections there for different components on the vehicle with guided tests. Okay. So what I'm going to do now is go back to our demo signal. Ben, you can cut this bit out while I just go back to the demo signal, please. So we'll start up again. Okay, I've just come back actually just a step because I think it's also useful if you are following along. I want to show you the guided tests first because it really is such a huge amount of information. But now I've kind of come back to the beginning. So without looking at the guided test, what I want to run through now, next I should say, is looking at just the kind of basic layout of our PicoScope 7 software, our waveform, and just starting to take some simple measurements. So I'm going to start again with the demo device. And we'll just minimize the toolbox for a moment. And here we have our 2 ignition signals. So I'm just going to move them apart. You might find when you open it up, you only have one of these open. So you might only get the first one, but you can turn these off and on if you wish to gain more signals. Right, so here we are. So I really just want to focus on the very basics here. So we've got, first of all, the scope, and this is the time. So this is the time we have along the bottom of the screen, and effectively that says 10 milliseconds per division. So that's 10 milliseconds between each of our grid marks on our screen. And then in terms of our voltage scale, we've got on this side, so our blue voltage scale is plus or minus 100 volts. So there you'll notice we're 0 in the middle, 100 at the top and minus 100 at the bottom. Our red scale comes over here, and that one is in amps, and that is plus or minus 2 amps. Now you notice you can't see the bottom part of the scale, and that is because I moved it. If I move that signal to the top, and as you can see now, we've got 0 in the middle, 2 amps at the top and 2 amps at the bottom. But obviously we can, one of the the really great things about Pico is you can move the signals around to make them easy to look at and analyze. So that is what we call our voltage. And okay, this often will show different things. So in this case, we've got amps, but we could be pressure here as well, and it just changes the scale. But we tend to call that the voltage scale, rightly or wrongly, and milliseconds, or our time base along the bottom, which in this case is in milliseconds. We can set a trigger up, and a trigger is just a way in which we stabilize a signal that's happening again and again and again. So in this case, we've got an ignition event, and we are looking at 2 on one screen. If I change my time base down, then we lose it. Or if I time base it up, you'll see we get more data on the screen. So you can play around with that as you see fit. And then we've got our buffers menu, and effectively what that means is whenever I press stop, we get 64 frames of data back through time. They will all look the same because I've stabilized the signal, but I promise you that is 64 frames of data. So yeah, so in terms of where we first start with, we are in here, and in terms of how we now work, and Phil has gone with you obviously through how BNC Plus works. So generally you don't have to choose probes nowadays, although we do still have the options here. If you've got older probes from your previous kits, for those of you who are lucky enough to have upgraded to the BNC Plus, you can still pick the BNC probes if you've got them, but obviously BNC Plus would automatically show you those. So for each of your 4 channels, you can choose the probe you want and you can do various things to the display, but don't worry too much about that now. Just think about the voltage settings and the probes that you may pick. But like I say, BNC Plus will make that considerably easier for you. When you press that, that menu just slides in. There are lots of other things in here, but don't worry too much to begin with. We'll go through these as Phil starts to show you working on vehicle. Just a couple of things that we should just look at. So we have rulers on both scales. So there you'll see, you just pull it across. You don't have, they're always there. So we could measure, for instance, between these 2 ignition events. So I'm just pulling them across there to the same part on screen. So we've got 60 milliseconds between those 2 points. You can be incredibly accurate. So over here we have our magnifying glass, and once we've got zoom in, you'll see you get this little lozenge up in the bottom right hand corner, and you can zoom in and then move your, so you can move your rulers to be incredibly accurate. So yeah, I'll just move those along so that we're getting exactly the same point on both. And you will notice that, yeah, it's still 60 milliseconds. So in terms of what options you have on zoom, you can kind of zoom in and out on the different scales. And then you can basically undo, which means you go back, or if you go 1 to 1, it just takes you back to the beginning screen. So lots of options there on zoom. Please download the software, just have a play with them. It's really, really very, very easy. And once you start to use it, you will find that it's quite easy to navigate around. Like I said, lots of different things down here that you can look at. Measurements and obviously rulers we've discussed. Channel labels. So, you know, you can pull down here. Once you start to do your own diagnostics, it's important that you'll see there all the different options we have around all the different components that you may find on a vehicle. And then any channel notes that you might have. But then also whether the waveform is good or bad, or if you're not sure when you upload it onto a reference waveform library, one of our guys will have a look for you. Something that's worth a look at is reference waveforms. So we can just add reference waveform of number A, and effectively what that means is if we were looking at 2 components side by side, so one of the things we're going to look at today is a coil and plug measurement. So you might want to take a measurement from coil plug A, create a reference waveform, and that effectively is what I've done. So I've asked for an A2, and A2 basically means it's a copy of number A. We can change that into every colour. So I think that's good, so I'm going to make that green, and then that will be there. You may not have noticed it yet, but when I move this down, you will see that an exact copy of reference waveform. I'm just going to turn off, that was as easy as it was just to turn off channel B. So all we've now got is, and I'll just get rid of the rulers, I'll just get rid of the zoom. So now what we've got is a reference waveform of channel A. So yeah, back to when you see the demonstration Phil's going to do on the coil and plug probe, you will see that he uses reference waveforms when we're looking at multiple coil packs together. So it's very easy. You can do coil pack number 1, save it as reference waveform, number 2, number 3, and you will notice when there's something different. To be honest, you very, very quickly build up your own knowledge of what good and bad waveforms look like, particularly with ignition signals, but it's really nice feature to start to use at the beginning to get used to creating a reference waveform. Okay, so a lot to take in there, I know, and that is really only the basics, but what it proves is that you can literally download the software for free now, even before you buy PicoScope, and start to work and understand how you would measure and manipulate a signal. Okay, just final thing on software. If you're not aware, we do make vehicle oscilloscope diagnostic kits for more vehicle manufacturers than any other oscilloscope manufacturer. So that's just a range there. If you look in the picture in one of our cabinets, you can see the sort of people we work for. We quite often get asked, well, what's the difference between the aftermarket oscilloscope that you would buy compared to a vehicle manufacturer? And the truth of the matter is, the software and the hardware is exactly the same. Indeed, a lot of the work that we do with our vehicle manufacturers drives our software forward, particularly as we start to move towards working with electric vehicles and as obviously systems change. The only thing that will change within a software is that sometimes a vehicle manufacturer will put their own waveforms from the vehicles they're working on in the place of where we have our guided tests. So that's something to look out for. Effectively, from an aftermarket point of view, you get exactly the same help and guidance through the waveform library, and we'll cover the waveform library yet, but that's where you can look for signals based around vehicle model, make and engine code from the vehicle you're working on. So like I said, Phil's actually going to take us through that a little later on. So enough about software, then we're going to move around to the hardware. In terms of connected components, so we do connect into the front. So in this case, we've got a 4-channel oscilloscope. So we put in test leads, that's our kind of standard test lead. And then at the end of that test lead, we put a range of adapters, clips and adapters. There's our backpinning probes, so that's something you're going to use all the time. Comes with all, even the most basic of kits. Then we have breakout leads, so we do a number of breakout leads. This is from a set of 12 different breakout leads. And then we have things like current clamps. Big advantage with our new BNC Plus connection is we don't need batteries in our components, so this will drive and not run out. And then we've got coil unplug probes, so we're actually going to have a look at working with coil unplug and a little bit with Phil. Then we've got our times 10 probe, round 2 pressure transducer, and then of course all of our NVH kits. So a huge amount of ways of connecting to the components. So what I'm going to do now, I'm going to pass you over to Phil, and he's going to run you through the main contents of one of our kits in a little unboxing session. Over to you, Phil.
Hi guys, we're going to talk about the 4-channel standard kit today. And here we have on the table in front of you our foam inlays. Please don't forget that the kit does come in a case, and one of those will appear on the picture very shortly. So let's talk about all the bits that we've got in the kit. So we're going to talk about initially the scope. We've got the 4425A with the BNC Plus connectors on the front, and we've got the USB port at the back. So what we do is we plug in our USB cable into there and put it onto our laptop. So that's how we make connections. So what we've got here is our BNC Plus connector leads, and we're going to talk about those. So what we're going to do is show you the 4 different coloured leads which come in different colours, and these come in either 3-metre long leads or 5-metre long leads. So we've got 2 connections. That goes onto the scope, and we're going to show you. Really nice connector, you can see there. To release the connection, you push those and let go. And then what we've got to do is do 2 things. We're going to connect that to an earth. So this is where we come with the crocodile clip for making good earth connections. And we are then have got our 4 different coloured leads, all the same colours as the scopes. So we've got red, green and yellow. All these, all the same, exactly the same. So you're now going to ask, how do we make connection to stuff? The majority of the time we are going to use a backpinning probe. So what we're going to do is we're going to connect that onto our test lead, like this. And we're going to go down the back of the wire, on a wire, we're going to push that down the back of the seal on the plug, and we're going to make connection. So again, we have all the different colours, and we have replacement needles inside, so that when they break, you just put them in. So that's the first way. We also have 4mm banana clips on there. If you're going to use other manufacturers' test leads, you may need those to connect with them. We have small crocodile clips here in different colours for going onto terminals of old-fashioned coil packs. And we have multimeter leads here. If you've got a very big connection like on a commercial vehicle that you want to get onto, you can use those. So we've got them all in red or black. We have here our S-hook, which is great for hanging the scope on the engine bay, but also for hanging the wires on so that you don't get them into the engine bay. So as John's talked about earlier, we're going to talk about current clamps. We have a selection of current clamps. So this is BNC Plus again, so no batteries included. So this is the 2060 clamp for doing injectors and all sorts of different components that we want to look at current draw. And then here we have the 2000 amps clamp. Again, no batteries, so you just open the drawer, put it around the cable. So this is for battery testing. Very, very quick, very, very easy. And here we have our magical coil on plug probe, which you will see us using later on for doing coil packs on petrol engines. But it's also very useful to be able to do other things as well. So we may talk about that later on. So ignition wise, if we have an older vehicle that has ignition leads on, we're going to plug that onto the ignition lead, connect that to the scope. Or if we have multiple ignition coil packs, where you lift the coil pack out and you put 4 of these on, what we then have to remember is to put the earth-in lead onto the coil packs. So one of the main problems that we have, like anything, is always connecting to vehicles. So not forgetting that we have a selection of different fuse extensions, which again, we can take the fuse out of the fuse box, plug that in there, put it into there, and we put the current clamp round there. And we have a little voltage takeoff as well. So these come in numerous different sizes. Very, very good for making connection to components in circuits. So we then have here, for many of you who have used our products before, you will have been aware that we had an attenuator that we used to stick on our leads for looking at primary ignition and also measuring flex ray. So again, we have the new BNC connector. Again, the 2 connections, very, very simple, very easy to be able to use on primary ignition and flex ray. So that gives you a little bit of an overview of all of the bits in the kit, and you can look on the website to see all these part numbers, and you can also use the app to look at all the applications that we've got. Great way to use a toolbox as a tool solution and to put all your bits of kit in there. And later on in the videos, you will see that we have a hanging boom on the back of the toolbox to put all our leads on, which is a great way. So, you know, they do come still in cases, and it's a great way to protect your kit, but also use it on a daily basis in a toolbox solution with all your diagnostic equipment. Okay, thanks.
Thanks, Phil. That was excellent. So just, obviously, as Phil's taken us through one of the main kits there, but there is a huge range. You can see them on our website. So just a recap, that's www.picoauto.com. Or more importantly now, download our app if you haven't already. So you can go on the iOS store and you can download our PicoScope app, and I'll cover that a little bit later on as well. But that really is the best way to view the difference between the kits. So we've got, just a quick recap there. So we've got our starter kit through to this being our standard kit, and then right the way around to our master kit. So a huge range there in the master kit. So let's just have a quick look at BNC Plus. And like I said, Phil's going to start working on vehicle in a minute, so you'll really see just how quick this makes it to set up to running a test. But effectively, if you've not used BNC Plus before, what we're doing is the scope is reading what we're connecting. So the minute you connect a current clamp or a test lead or anything else, the scope actually knows. So this is much more different from a standard oscilloscope with a BNC connection where you've got to tell the software what you've connected. Effectively, the newest versions of PicoScope do that all for you. So effectively, you plug in, you plug in the component you want to use, and then you can go straight away into testing. And more importantly, we have something called probe mismatch. So if you do go wrong, it'll push you back on the right line. So it really, really does make the setup and working with PicoScope really, really easy, particularly for new users. But even for more advanced users, what we've noticed is that they just like the speed they can set up. It just makes the whole diagnostic process that little bit faster, and that's good for everybody, no matter what your level. Okay, so that's kind of the basics. That's looking at our oscilloscope, that's looking at the kits, and obviously introducing the software. Of course, the most important thing is really working on vehicle. And we're going to start that now. So for each of the tests we're going to do today, we're going to try and break it down into three sections. First is connection, so how we connect into that component. That can seem quite daunting when you first start with PicoScope. Don't be. Actually, the first test that Phil's going to show us today is multimeter versus PicoScope. So I'm sure all of you will be using multimeters, and actually connecting to that component with a oscilloscope is no harder, but what you see is so much more valuable. So connection, then run, what we call running. So we are capturing our data, collecting our waveform, and then moving on finally, and this is where we'll spend a lot of what we're talking about today, reading those waveforms and understanding what to look out for when things go wrong. So we'll do each of those sections. And just one final note, in case we forget to say it later on, we don't put any power through the scope back into an electrical component, so perfectly safe to use. So you can't fry an ECU by using PicoScope. It really is safe. Of course, as we'd always say, use the guided tests to help you understand and do the test correctly. Okay, so connect, run and read. So we're going to have a look at multimeter versus PicoScope now. And I'll just take you very quickly through the process, and then Phil's going to work live on vehicle. So effectively, as I just said, this is exactly the same as using a multimeter connect to a component, but what we're going to see in the waveform is so much more valuable. Phil's going to show us a camshaft sensor. So let's just have a quick look how we're going to connect into it. Normally, most standard way would be to use a back pinning probe. I think in Phil's case, he's going to have used a breakout lead. We're just lucky to have all the breakout leads for the right components here set up. So we're going to connect in and we're going to run. So effectively, we've got to have the engine running on idle to capture our data. And then read. So when we look at our multimeter, there we go. We've got 12.16 volts. So if you have a look at that very quickly, you'd think, oh, well, that's a 12-volt sensor. Actually, it's not quite as simple as that, and I'll just show you what we see when we look at PicoScope. So connecting in the same way, so as Phil will do here, we literally piggyback through that backpinning probe with a multimeter and PicoScope. And again, we're running with the engine on idle. All we have to do is just tell the software, so press go on the software and that will start to capture our data. And then we're going to see something like this. Not hugely clear on this, and it will be much clearer when Phil shows you, but actually this is a 16 volt sensor, quite unusual in this example. Why does the multimeter say 12 volts and PicoScope's telling us 16 volt? The truth of the matter is, if you look at this Hall effect signal, so it's turning off and on, basically the multimeter can't work fast enough. So it just averages, so it just takes the average line. As you can see, in this Hall effect signal, it's more on than off. So we get that averages out to 12 volts. Okay, I think that's probably enough of me for a short while. So we're going to pass you over to Phil now, and he's going to take you through multimeter versus PicoScope on a camshaft sensor. Over to you, Phil.
Thanks, John. Hi guys, right, so what we're going to do now is we're going to connect onto the component. So I'm going to take my red test lead, BNC Plus. So of course we're now going to put that onto our scope on channel A. And then I'm going to feed my wire around. The most important bit is earthing. Always take a really good earthing position. So because the battery is actually on the back of this car, it's in the back of the boot, we can't get to it. So what we're actually going to do now is we're going to go onto this crocodile clip that is on this lovely big earthing point. So what I've got to do is plug in my multimeter, turn it on, and here we have our sensor here. We've taken the protective cover off the back, and we've got one of our flexible backpinning probes that's pushed in there, and we're now going to plug in our test lead onto there, and we must just remember to plug in our voltmeter. So we're now going to come to our software. So we've got our software and we've got our guided tests. So now we've never done this test before, so we're going to go sensors, we're going to go camshaft position sensor. On this particular vehicle we know that it's a Hall effect signal, so we're going to put Hall effect. And you're then probably going to go and say, well Phil, how do you know? Well, majority of sensors that we're going to see are going to be either Hall effect or inductive. So we're now going to go guided setting file. And this is going to load the file that John showed you. So here we have our help file, and it explains how to connect, and you'll see onto the earth, making connection whichever way you want to, either backpinning probe, breakout lead. And then we have the software. So we've got the software here. That's the example we've got. Notes about the waveform, a little bit about the waveform library, how the sensor works, conditions, and also a little bit about diagnostic trouble codes. So we're now going to shut this, and we have here our voltage here and our time here. Now we know that although this is a guided test, we know from previous that actually we're going to have to increase the volt range because we know that it's more than 10 volts. So actually what I'm probably going to do is put it to 50 volts, and then I'm going to push the start button and John's going to crank the engine over. Okay, so if we look at the scope, I'm just going to stop the scope, and then John's going to look at our voltmeter, and we can see 12.7 volts. So let me just turn the vehicle off. So what we'll do is we'll zoom into this waveform that we've got on the screen. So you'll notice let's just go over to here. And this is the beauty of the PicoScope, that we can actually zoom in to this particular point. Now, you're probably going to say, Philip, why have you gone to 50 volts and not just 20 volts? Well, if you see here on this particular waveform, you'll see that we've got some interference. And we'll talk about interference a bit later, but effectively all we're doing is we're looking at this Hall effect, opening and closing, opening and closing. And as John has said, if we bring down our ruler onto here, you will see that we've got 14.98 volts, and our voltmeter was giving us a reading that was different. So, you know, very important to see what there is. The next thing to do is always save your information on the screen. So you can go vehicle details and populate this, because you want to save as many things as you possibly can so you can look at it later. Save all the details, save it on your desktop, and you can always then look at it later on. Not forgetting that on the bottom of the waveform here we've got our sensor, whether it's good or bad, and we can actually put in our wiring details of what terminal it was on the connector and what the colour of the wires were. So, but you know, as John has said earlier, you know, we're just reading the voltage that is there. No different. The point is that we've got 4 million dots across the screen, and this is really where the voltmeter cannot cope. It's just averaging everything out. So we're looking at the on and off switching of the camshaft sensor and comparing it. Remember, save what you've got, and we're going to talk about the waveform library later. Thanks, John. Back to you.
Thanks, Phil. That's excellent. Okay, so just to recap there on screen in terms of where the information is. So there's our guided test. So like everything that we showed today, there's an ABS speed sensor, just an example. And of course, there's our guided tests there on the left. So just to recap, we've got all of our charging and starting, our sensors, our actuators, right the way through to communication networks, electric vehicles. So huge amount of information in software to help you get going, operating and working with PicoScope. Okay, so we're going to just step sideways just for a moment. So there's a little bonus bit of software you get when you download PicoScope 7, and that is our Pico Diagnostic suite of tests. So this started off really as a vehicle health check piece of software. It's now evolved also to house our MVH and our balancing software, but the vehicle health checks are still in here. So we're going to have a quick look at this with Phil. So effectively we have the same help in here. We have help files, so it shows you how we connect and how we capture our data. So again, we've got these nice little diagrams. So we're going to use 2 channels of PicoScope. So we've got channel A is literally 1 test lead across the positive and negative of the battery. And then we've got our 2000 amp current clamp taking around the battery positive cable coming away from the battery. So that's how we connect it. In terms of how we start to capture our data, same as we would with any other battery test actually. We've got to tell the software what we're testing. So if it's a 12 or a 24 volt system, what type of battery we've got, what the ambient temperature is within the building we're working in. Actually, thankfully, you join us. It's spring here in the UK at the moment. It is lovely to be sitting in the workshop with a t-shirt on, because that hasn't been like that for a very long time. And then obviously our cold crank amps, so on and so forth. So very simple. If you've operated a battery test before, this will be very, very simple. And then we run, start the engine, and it analyzes basically the condition of the battery and also the charging and starting systems. So we will then get this sheet, and this effectively, they're your 2 waveforms, so the same as you would have seen them on the normal oscilloscope software, but then we've analysed them. The software's basically analysed them from green, which are good, or if you've got amber, might be something you want to look out for. And of course, if we ended up with a red dot, then we know we've got a problem somewhere within either the battery or the charging and starting system that's going to need attention. And one final trick up Pico Diagnostics sleeve when it comes to battery test is this really, really nice A4 test sheet that you can give to your customers, so you can fully customize this. You can put your logo on, you know, your garage logo, you put your own details in, and then you can print out. And like with everything Pico, the testing you do is time and date stamped. So yeah, that's something that's really cool. Okay, that's the theory. We're going to pass over to Phil now, and he is going to show us battery testing with Pico Diagnostics.
Right, so the first thing that we've done is we've opened we've closed Pico 7 and we've opened up Pico Diagnostics. And you'll see the very important thing that you see here on the screen is PicoScope 4425A has successfully opened. You always have to remember not to have two versions of software open, otherwise it will not find the program. So what we're now going to do is we're going to go to battery test, and what we've done is connected onto channel A onto our battery, positive and negative, and we then put our current clamp, our 2000 amps current clamp, which of course is lovely now because it doesn't have any batteries in. So we're going to plug that round there. And what I'm then going to do is I'm going to put my temperature probe onto the battery just to see what ambient temperature we've got. And as you can see, 13.8. So I'm now going to go onto my screen and I'm going to go battery test. And the first thing you may want to know is, if I can't remember how to do my test, what do I do? So, tests, and then battery. And then we can look at connections. Let's just make that a bit bigger so you can see it on the screen. So that it's exactly as what John has said previously, how we do the test. So all the information is there. So now, what we're going to do is we're going to go voltage on the battery. It's a 12 volt battery. We do have 24 volts if we need to. It's a lead acid battery, and from our readings before, it was 13 degrees. So we're now going to drop down to 13 degrees. And then what I have to do is just look at the battery to see what my CCA is, or EN. So we've actually got 680 EN on there. So another important bit of information. So we're now going to put in here 680 SAE, and we're going to push the start button, and then John's going to start the car. So you'll see that we're looking at the information on the screen, and after its predetermined level, okay John, you can turn it off now, we can look at the information on the screen here. So state of charge, okay, initial voltage, we can look at resistance, we can look at ripple, we can look at all sorts of things. Really quick and easy to see exactly what's happening onto the vehicle. Battery is good but may need charging. Yeah, the vehicle hasn't been run for probably 2 or 3 weeks, so yeah, it may be. And it is a really quick way of looking at how the battery test works. If we go to File, Print Preview, you can then look at exactly what there is, whatever test you're going to do, and the customer gets this really nice A4 sheet of paper which you can put all the vehicle details in and the company name and give it to the customer. So really, really great way of doing things. So hope you've enjoyed that, and very quick non-intrusive test for testing batteries.
Thanks, Phil. So yeah, really, really powerful test, added value to PicoScope. Yeah, working with Pico Diagnostics battery testing. We're just going to move back to PicoScope 7 now, and while we're talking about vehicle health checks, just going to show you a very short animation and then an example of a relative compression test. So again, really, really simple and really powerful, really powerful test in terms of vehicle health check. So in our short animation, this is one of the animations that's in our app, so our top 10 tests of working with PicoScope. So single channel test, so it's the same connection, but only one channel as we just did with the battery test. We don't want the vehicle to start, so that's why we're removing the fuse from the fuel pump. So we're running this on cranking. And what we're looking for here, if everything was working correctly with the engine, we'd get a really nice, crisp and even sawtooth pattern. But as you'll notice in there, we ended up with a missing tooth. So now we're going to use our coil on plug measurement to actually try and work out which of the cylinders. So we know we've got a problem with compression in one of the cylinders. So really, really simple test. We can check out whether there's a compression running issue, and then we can use an ignition event to work out which of the cylinders we'd need to go and have a look in more detail. I'm just going to show you this picture and this waveform. This is from a series called One Waveform, One Picture on our forum. And I think a picture paints 1,000 words. So what we would expect to see if everything was running correctly would be nice and crisp and even sawtooth pattern. But look, we've got this missing tooth. And there's the picture. Don't think I need to say any more. Our 4-cylinder engine, and clearly we've got a problem with compression in there. So just a really simple vehicle health check that we just wanted to show you on the back of battery tests. So PicoScope is not just about fixing known faults. Actually, when you've got customers coming in, you can give a car a really, really quick and easy vehicle health check, non-intrusively. We've not taken, we've not had to take even the cover off an engine to understand what's going on with the engine on the inside. Okay, so we're going to return back now. We're going to look at ignition. Actually, we did just see that in the relative compression, our coil on plug probe. So again, it's a we've got a single channel being used, so we're going to use channel A with a coil on plug probe. In terms of connecting, simple as that, we plug it in and we literally locate the top of the coil pack and we place the coil on plug probe on the top. This is really important, and Phil will show you in a minute. Really important that you get it nice and central on the top of the coil pack so you get a nice clear signal, and also if you're comparing one coil pack against another, you keep it in the same place on all of them. In terms of how we capture our data, we need the engine running on idle to run this test, and we're going to just pop that and capture our waveform. Our waveform's going to look something like this. Hopefully you're starting to get used to the way these waveforms look. This is a zoomed in image. So if you look on the top right-hand corner of the waveform there, that's what we capture. We capture our waveform over a number of cycles, but then we can zoom in and actually see everything that's going on within that ignition event. I'll just refer you now, if you're not sure what's going on with a waveform, go back to those guided tests. And within the guided test, we will show you what each part of the waveform is, and this is a really, really nice one with a coil on plug, so we can see and measure what the burn time is. We can see the coil oscillations at the end. We can see everything that's going on with that coil pack to understand that it's working correctly. So grabbing and capturing our waveform and then referring back to the guided test, you start to understand why the waveform is the shape that it is really, really valuable in starting to build your own understanding of waveforms. So we'll have a very quick look at another animation because I think it's important, and then Phil's going to show us live on vehicle. And again, the animations really give us a nice way to show exactly what's going on. So we're just simulating here a problem with our coil pack. So this just shows you exactly what we're going to show you live on a vehicle, just checking one coil pack against another. Just gives you a nice example of what does a waveform look like when things don't work perfectly. So we're just using a reference waveform here. So remember I showed you earlier when I was doing the quick run through on PicoScope 7, we can capture a waveform and hold it on the screen and then compare our bad one. So look how different things are. So effectively in this case, what we've got is a coil pack that's not storing the energy correctly. And it's obviously not got the power to fire the spark plug. Most important thing with everything Pico, and we're going to kind of get onto this as we kind of get into the second half of our presentation today, once you've replaced the component, testing it with PicoScope to make sure that it's now working correctly is absolutely key. So another one of our great animations from the app and also on our YouTube site really does give you a nice understanding of where you fit PicoScope into everyday testing. Okay, let's go back over to Phil and he's going to show you coil plug testing with PicoScope.
Thanks, John, for that. So first thing that we're going to do is we're going to make connection. So we've got our coil on plug probe and we've connected it onto channel A, and we've just rested it on the coil pack, in fact. So what we're now going to do is go to the screen on the laptop and we're going to go here, ignition system. So we're now going to go coil on plug, millivolt scale, and we're going to load the guided tests. And as you'll see here on the screen, this is exactly what John showed you earlier. So you've got how to connect, the little video, what we're going to see, examples of the burn time, other relevant notes of how the coil pack energy is stored, and then we're going to look at all the information about how the system works and further guidance, and of course we've then got the waveform library that we can go back to. So what we're now going to do is close that. Right, okay, now let's start the software, start the car up. So you're going to see when John places this on here, just the different readings that we can get and how he moves it around. You'll see that we've just gone over scale there. So there are occasions when you may need to change the millivolt scale, but we're looking at the operation of the coil pack, and you'll see it really does depend from when John's got the camera on the screen about where or not the probe is positioned. So please always remember to position it in a good place and play around with it and see what you can get. But you know, the most important thing is that actually it's not just for coil packs, it's for other actuated components, injectors, EGR valves, and even EV charging connections. Thanks, John.
Thanks, Phil. Excellent. So what we've tried to do there is just show you some really simple examples of the kind of initial tests you can start to undertake with PicoScope, and then effectively they just become building blocks for more advanced testing. And of course there's loads more information online about testing lots of other components. So what we're going to try and do now, we're going to run you through a couple of case studies. Just to give you an example of where PicoScope is going to really help you with everyday diagnostic problems that literally, as I just said, are going to be every day within a workshop. So I'm going to start with cam and crank position sensor correlation. And often we get told that this is a main reason for buying a scope. So I'm just going to take you through the process, what we look out for, and really how we look at timing using the scope. This is a fairly bog standard fault code, so P0016. And we, just because, you know, we sell oscilloscopes, we recognise that we're just one tool in the toolbox, and it's really important that you have access to good quality serial diagnostic data, as well as, you know, technical data, as well as good training as well. So we've taken our fault code in this case, it's given us this issue, and effectively, as is not unusual, the customer's brought the car in, saying that there's been a fault, a dashboard light, ever since the car had been into a different garage for a cam belt change. So we were actually called in to try and have a look at the cam and crank synchronisation, and to show the garage actually how you apply PicoScope to looking at this fault. So we're going to look at the cam and crank operating together. So it's clearly a two-signal, two-channel waveform we're looking for. So just for those of you who aren't aware, so we've now got our crankshaft sensor. Our crankshaft sensor there is at the top, that's our red signal. And then our camshaft is our blue signal. Now that's quite different to the camshaft sensor that Phil showed you on the car we're working on here. And that's quite normal. You know, there are thousands, literally thousands of different camshaft signal. It's really where the waveform library can be really, really powerful for finding a good known waveform from a cam and crank sensor, can really help you with your diagnosis, particularly when we're looking at timing, engine timing issues. But actually, in this case, it was even easier. So actually, if we look at here, in our crankshaft signal, we expect there to be a gap. There is a gap, a natural gap, as you'll all be aware, in the flywheel. So there's like a missing tooth. And that is how the crankshaft sensor understands where the timing is. And we expect there to be a gap in the flywheel here, and we expect to be the gap in the flywheel. That's a really, really bog standard crankshaft signal. So once you get used to the fact that each one of these other little raises is a tooth on the flywheel, it's very quick and easy to diagnose what the problem is, because look, we've got an extra gap basically within every revolution on the flywheel. What causes that? Well, actually it's really, really simple. So I'll just zoom in there. So again, power of PicoScope, we capture our data over a long period of time, and we can then zoom in on the detail. It's fairly obvious when you start to understand waveforms, and as you build up your own understanding, you see a fault like this, you know what your fault code is, and it's clearly that one of the teeth on the flywheel has been snapped off, probably why the cam belt had been changed, so they've just held a bar in the wrong place and it's just clipped a bit off the tooth. From a cam and crank correlation point of view, the sensor now sees two gaps every revolution, and it's just going to throw it out. So actually, really, really easy to diagnose. Same thing from a connection point of view, it's going to be two backpinning probes in each of the sensor, look at them together, and away you go. This is another example, very similar. This is again from that one waveform, one picture thread on our forum that I showed you about earlier. So we'll put a link on the video as well so you can get to all those. It's really, really nice to be able to see the faulty component against the waveform. So have a look on there, it will show you just where PicoScope fits to problems you will see daily in the workshop. And most importantly, you're analysing all of this and understanding before you've even removed the bolt. So, you know, we're doing all this unobtrusively, connecting to those components and building our understanding of what's going on within the engine or within the vehicle. So there you go, that's just a zoom in and showing an example. Now, what I'm going to move on to now is the kind of next part of it. So if we've got in this case, two really nice crisp waveforms. So again, just to talk you through, so we've got our Hall effect square edge waveform. This in this case is our crankshaft sensor, and the blue one is our camshaft again. I'm now gonna take you over, we're gonna have a look at the same waveform, but I'm gonna show you it within the software, and I'm gonna talk to you about how you measure cam and crank correlation. I'll start to build up a view, perhaps if you've got a slip belt or a stretch timing chain, you can see it with PicoScope. And that really shows you just how valuable those 400 million samples a second are to you. Right, we'll go over to the software if we can. Okay, we're going to have a quick look at the cam and crank signal. But bear in mind, when you're talking to workshops and technicians, you'll probably get asked a question about using an oscilloscope to look at engine timing. Effectively, that really means we're going to look at cam and crank sensors together, as long as sometimes with an ignition event. But just for this demonstration, I'm just going to show you how a technician would look at a cam versus crank signal. And I'm going to use the system signal from one of our guided tests. So we're going in here, systems test, camshaft and crankshaft position sensor. So we're here. So we do the guide and the settings file. So obviously, you know, show them the guide, how they make the connection of the two components. And obviously, you know, we've been through the rest, you know, waveform notes side by side. And actually also here looking in the waveform library, so for the customer when he's looking at engine timing issues, being able to get onto the waveform library and to search for a cam and crank capture from the vehicle they're working on is absolutely critical. So, you know, if you've got PicoScope connected, you can go in the waveform library and download a signal. But like I said, for today, I'm just going to use the signal, the waveforms that are housed within the guided test. So that's all that. So we'll move that up there out of the way, and hopefully everyone can see that okay. So point here is we've got two signals. For those of you that aren't aware, the red signal is our camshaft signal, and it does show you down here, and the blue is the crankshaft. For me, I'm just going to separate these a little bit, just makes it a little easier to see. Now it's always easier, or tends to be easier, to look at the crankshaft position sensor first. So we always have this gap, if you see, here to here, and this is one rotation of the flywheel, and that is actually the gap that you see on the flywheel, and I'm going to show you a little example of that shortly. So we take one of these points as a reference so we bring our rulers across for the crankshaft. And then on the camshaft, we're going to look again for a point of reference. Now it's not quite so obvious as it is with the crankshaft what the repetition is, but I promise you it will repeat. So what we try and look out for is a pattern. So we've got what we call here rising and falling edges. So we take our rising edge, and then there's kind of a really small gap before it drops again, and then as we get on our rising edge, a larger, and then another rising edge to another larger one, another rising edge to a larger one, and another rising edge, but now to a medium, and then we're back to a small one. Do you see what I mean? So actually the rotation of the engine from a camshaft point of view is going to be from here right the way across to here. Don't worry too much about that, because from a cam and crank position sensor point of view, you're just going to use a point on the camshaft signal. So in that case, I'm going to use that rising edge to that really small one. Yeah. So I've brought my rulers across. Really useful here. By all means, bring in our zoom so we can be really accurate with our measurement. I am going to use the base of that rising edge of the waveform and just move this one across. Okay, so that is our crank to cam, and that's obviously the zoom overview, and you'll get used to being able to kind of nip in and out to view the whole thing. So where we've got the difference between those 2 points is actually 8.97 milliseconds. So if we'd got a stretched belt or timing chain, excuse me, you would notice a difference. This is a good known waveform. So if we've got a good known waveform from the waveform library, and the capture from the vehicle that the customer is working on is different, you then know that something has moved, whether that be, you know, like I said, could be a stretch chain, could be a belt on its way out. And there's a really cool thing here. So we can actually lock those 2 points together. And just for fun, if I move that over, so to the end of the next rotation, you will see that the next point where we line up that part on the flywheel to the camshaft sensor is exactly the same. But just bring it back here. And one final point to note, just to remember, or just to be aware of, and I will just zoom in here just to, so we can have a good look. So just zoom in there just to the capture. Notice from that point to that point, each one of these raised points on that crankshaft waveform is actually a tooth on the flywheel. So actually, if something has moved, has shifted either left or right, you would know. So you can actually count the teeth. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So that is 8 teeth along from that point. So if this if this measurement was over here, so the rising edge was here, you'd then know, or the technician would then know, that there has been a change and something has slipped, and that may well be the answer to the timing error. So really, really simple test. 2 sensors, 2 backpinning probes connected, and you can look at engine timing. Please have a look online. We go into this in more detail in some videos on our YouTube channel, but a really, really useful one to open up, to practice using the software and working on engine timing, looking at PicoScope. Hope that helps. Okay. Hopefully that made sense to you, and it really shows you where you can apply PicoScope to cam and crank faults. Okay. I'm going to show you another one now. We get asked a lot about particularly CAN faults, but with Pico, as I'm sure you're aware, you can do all communication systems. You know, we can look at FlexRay, everything, as I've said before, everything with a wire, everything with a signal we can look at with PicoScope. So we're going to look at a CAN communication fault here on a Mazda 3, and I'm going to pass you over to one of our other technicians, Ben, who actually was called in to look at this test, and he's going to talk you through a Mazda 3 CAN communications fault on the little Mazda. Over to you, Ben.
Hello, my name is Ben Martins and I'm one of the automotive application specialists here at Pico in the UK. And today we're going to look at a previous case study that we have on our website. Now this is the Mazda 3 CAN communication case study that I did not long after I joined Pico. Now what we've done is we've actually gone over it. We're going to obviously put it into video format, but also look at some of the things that we may not have missed, but may be able to, having the ability to review Pico files gives us the opportunity to look back in time and see, was there something else there that we maybe have missed? Is there something that we could have learnt from it as well? So this is what the case study is going to be about going forward. So first of all, we have our customer interview. So when we pick up this particular case study, I was invited to join a workshop. They've had a vehicle in for a very long time. It's a Mazda 3 diesel, and the fault, according to the customer, was that intermittently the RPM needle drops to 0 and all the warning lights on the instrument cluster appear. So that was our problem. The flip side to that is that once it does that, the only way to get back to normal is to cycle the ignition key. So switch off and back on and everything is fine again. Now, also talking to the customer, because the customer has all the answers until they don't, we also found out that the vehicle had been involved in an accident. Now, whether or not that's something that that could impact our fault is yet to be seen, but ultimately that is important information to have. The fault is not specific to weather conditions either, so it's not temperature related, it's not affected by rain, it's just very sporadic. And I think the intermittency of this fault is the key point to this particular case. Sometimes it can go for 100 miles plus, sometimes it could be literally just driving it round the corner and the fault would occur. So there was no real, really an easy way to replicate the fault. So again, important information from the customer. Also from the workshop, we found out that they'd replaced a number of ECUs and it still hadn't fixed the issue. So the next step of our diagnostic process is to verify the fault. Intermittent faults are by far the worst that you can possibly encounter, because you can guarantee that as soon as that vehicle arrives in your bay, it's not going to act up. So what we'd done is the vehicle had been with the workshop for a number of weeks prior to us attending, and they'd cleared the faults down and then driven it around for a bit, and then the faults had reappeared. So rather than clearing them down again, that's when we got invited to come and have a look at the vehicle. So we were seeing it in its faulted condition, even though when the cycle of the ignition key had happened, obviously all the warning lights had gone off. However, all the fault codes were still in the ECUs present. Now, there was a number of fault codes that existed. A lot of them are all U codes, which indicates that it's a communication fault. A key bit of information here as well is that it's multiple ECUs reporting different losses of communication. So it may have been the engine ECU has lost communication with the ABS ECU, the instrument cluster, front radar, front forward-facing camera, etc., etc. But then they would also report communication losses with those ECUs as well. So the instrument cluster would report a fault with the engine ECU, and so on. So that just starts to help build a bit of a picture as to what's going on. I mean, there's no real way that things can point their fingers at. So sometimes an ECU might record a fault code, and that gives you some direction. In this case, there isn't any direction at the moment. The next point of the diagnosis is to gather your technical information. So long before PicoScope gets involved, there's a lot you have to do before you get to the point where you actually take a measurement. And that is so important because it helps build your action plan, which we'll come on to in a second. So technical information and data is massively important because it can help streamline your diagnosis. When it comes to CAN, one of the most important bits of data that you can get is the network topology. Now basically this is an overview, kind of like a bird's eye view of the network as it's in its entirety. So rather than having all different components connected, it's just purely looking at the connections between ECUs and where they sit on the network. That can be really helpful with identifying things like end-of-line resistors, which ECUs have the termination resistors in place. And from there you can start to think about, well, where am I going to start to measure in order to try and diagnose this particular fault? So your action plan, what are we going to do? So given that the fault is, well, it's a loss of communication, you could argue, well, I'd start the diagnostic connector. If we just go back a page, we can just see here that the diagnostic connector sits pretty much bang in the middle of the network. Now, we could go there and make the first measurement, but this is a loss of communication between two ECUs, like I said in the first part, between the engine ECU and the instrument cluster. They were one of the fault codes. Well, you can see here the engine ECU is right at the top of the network and the instrument cluster is right at the bottom. So going bang in the middle might not be the best point to start at. So in this situation, what we decided was to go at one of the ends. Now, the easiest access point in this situation was the front body control module. We'll just flick back a slide again. The front body control module is the first ECU after the engine ECU. So it seemed like a good place to get to. It was one of the easiest ones to get to as well. And we could use backpinning probes through the connector to actually get onto our CAN high and CAN low. So from here, very, very simple. We can use a guided test to look at the physical layer to see what that network is doing. So now we're at the point where we take a measurement. So this first capture, what have we got? Well, standard looking CAN really. It looks fairly straightforward. In this particular capture, I actually have CAN high on the red, which would be channel B, and CAN low on channel A. Typically now we like to make sure that's round the right way, just for the maps channels that we might use to help give us some more information. However, it's not a problem. You can create your maps channels as you go. When we subtract CAN high away from CAN low, we're left with what the actual ECU is seeing. CAN is a differential network, so by subtracting one away from the other, we are left with a very clean signal, which is what the ECUs are doing their decoding on. Even from this very first capture, there is a number of things that we may have not missed, but may have overlooked when we first did this case study. Knowing what I know now, and hindsight is a wonderful thing, of course, there are some little key points here which could have helped us even further to actually start understanding what was going on with this network. So the first thing we notice here, and I'm just going to flick to the actual file itself, is we can see here that this is our CAN capture on the left-hand side. All I've done is I've added in my A plus B. So by adding the two together, we can see any voltage differences between CAN high and CAN low. If everything's good, they should be the same. If we have 2.5 and 2.5, we get 5. If we had 3.5 and 1.5, we should also have 5. So regardless of whether the network is in its idle state or whether it's transmitting, it should be around about 5 volts. There is some fluctuation, we can allow for that as well, so don't worry too much. What we do notice in the A minus B, or CAN high minus CAN low, so there's differential side, there is quite a lot of ringing still present. So if we look in these two raw signals in the red and blue trace, we can see that there's some fluctuation. There's some disturbance during a bit or a transmission of some data. We can also see it in the differential side. Now, if they haven't cancelled each other out, is that a problem? So one way to verify that first is, of course, make sure that your measurement is good. There will always be some ringing within a CAN network that you're measuring because it's due to the actual leads that you're using as well as the physical network itself. So you will see some ringing. It is there. It's a physical phenomenon that's going on. You could verify this by just making sure that it's not your leads that are causing the issue. So one thing we learned now is that actually our ×10 leads, our high impedance probes, can really help clean up a CAN signal by reducing the amount of ringing that we see in the signal. So that would have been position notes or test number one, like verify your leads. I could have gone back and just made sure that this is a real phenomenon. This is something that is an actual problem with the network, or isn't it because of our measurement? So bear that in mind in the future. Because we captured a number of waveforms using Pico, we can now obviously move back and forward in time from our capture. And we just moved through the buffer just to have a little look at some of the other messages that we've captured. Now in this instance, with this particular capture we have now, the ringing is no longer present. So there is no disturbance within the CAN. So now could we say, well, actually our test leads were okay for this particular measurement, and in this situation, is that ringing actually a problem? You know, again, this is something that we overlooked a little when we first did this case study, but it's something having the ability to keep those Pico files and then many years later actually review this can actually help you learn more. Again, moving through the capture, we can finally see that we get to a point where something's wrong. Very clearly, something's wrong. It looks, to begin with, that the actual message does start together and is lined up. Then all of a sudden, there is a dramatic shift with CAN low. And that's reflected clearly in the A plus B and also in the A minus B as well, so the differential part. So what does that tell us? Well, clearly we've got a problem. It also means that the only way that you could particularly have, shifted packets, especially between can high and can low, is if there's something physically wrong with the line or the communication line. It's not like an ECU is corrupting the data as such. Something has shifted. So how can we prove that? Well, with a 4-channel scope, we have 2 extra channels left. So the next point was to update our action plan. Going back to our topology, we now looked at the best and most easiest point of access to another part of the network. Now, really, there was possibly some other places we could have gone to, but actually removing the instrument cluster in this situation seemed like the right thing to do. It was the very, very end of the network. It wasn't too difficult to get to. So once we'd got the instrument cluster out, we then used channels C and D on our 4-channel scope to measure can high and can low at both ends of the network. Now that gives us the ability to now watch what's happening with each packet as it's sent over the entire network. So if the engine ECU, for example, sent a message, we should see exactly the same message at the instrument cluster, be there an ever very small timing gap between the message being sent and the message arriving. So with that in mind, we can start to build a bigger picture of what's going on. To begin with, everything looked okay. Yeah, we've got our can high and can low at both ends of the network, and they look pretty similar. One thing again, having the ability to review our P-code files is helpful and useful. We can see that actually in the A and B channels, which are closest to the engine ECU, remember they're at the front body control module, there is quite a lot of ringing effect. Yet in that same message at the instrument cluster, everything is okay. Now we could go a step further and actually decode these packets. We didn't need to at this point, as you'll see in a second. However, we could have seen what was the message, and we could have gone a step further, and if we had the information, actually worked out where that message had come from. So again, there's just some visible things with these 2 signals that we can start to go, well, why is one different to the other? Finally, then we start to see the real fault as it appears. Now, in this situation, we have 2 different messages which are on the same network. Now, that is not possible. They should all be timed correctly. The only thing here that can affect and cause this particular problem is if there is a problem with the physical connection to both ends. Yeah, so there is something that's happened that's changed the way the 2 messages are being sent on that network. They should be the same, they're not. Structure-wise, they actually look okay. There doesn't seem to be any real corruption between the 2. It's just that there is a massive off shift. Also, when you look more closely at these 2 captures, you can see that the data is very different as well. So they are 2 different messages being sent at 2 different times on the same network. Again, we can prove this one step further by adding in a decoder to actually show the differences between the 2 and see that those IDs are different as well. Okay. So, next part of your action plan. We've found out what is causing the issue as such. We found a problem with the CAN network that can lead to a loss of communication between ECUs. It's now a point of finding out where that issue is. Now we suspect a hardware issue. When I mean hardware, I mean physical connections between can high and can low somewhere on the network. So how can we start to move in closer to it? Well, the easiest way is to find additional access points to actually start measuring at. So we then moved our channel A and B to slightly closer, where we got onto the DC-DC converter and another control module, and then we moved from our instrument cluster and moved into the network slightly. So we gradually sort of moved in and basically trying to isolate where the problem stops or doesn't exist. So if, for example, we'd moved the other side of where the problem is, then everything should be same. Everything would all be lined up as we'd expect. If we go back and start to see that separation of network packets or communication packets, then we can start to see, well, the issue is in this area. Now what we found when we started looking a bit closer at the wiring diagram was actually there was a point where the front forward-facing camera in the windscreen, the network actually did like a loop. So rather than just being a branch coming off, going up to the front forward-facing camera and the radar, the laser guidance, actually what it did is it came in up to the front forward-facing camera module and then back down again. So it's like a big loop. So it's kind of like done a loop round and then come back. This was all contained in just one plug. So it seemed like the right place to try and go to next. So behind the A pillar, we found out that the connector was not fully depressed all the way and it wasn't connected. So it was literally just resting on the top of the pins. Now, when you look back at the captures, you can start to see why that was, how the fault had manifested itself with the captures that we were seeing with Pico. So if you imagine you're driving along, you may hit a bump in the road, all of a sudden that plug just momentarily loses connection. That is more than enough to cause all of those fault codes. Again, once you've come to a stop or cycled the ignition, that may have rested back again just so that it's connecting with all of the terminals. Ignition back on again, everything's happy. So once we clipped it back in, we heard an audible click just to indicate that it had locked together. Went out on a road test, and obviously the validation from your testing it would be your next point of call. So go back over, just make sure that the whole thing is working as expected. Now, given that this was an intermittent fault, the vehicle was left with the workshop for a number of days. A few more miles were put onto the vehicle as the customer allowed, before the vehicle was handed back, and everything was fine. So let's just go back in and just look at some of these captures between these, where we have our 4 channels. Now, I just wanted to just pick up on this ringing effect that we were noticing. So if we zoom in slightly, and all I'm doing there is just using the mouse wheel, just zooming into the capture, we can see that actually where we have our C and D, so in this case, this was at the instrument cluster, channels A and B are up by the front body control module. We can see here that actually there is some ringing near the front body control module and no ringing near the instrument cluster. However, let's look at the end of frame or the acknowledgement part of the packet. Now we get lots of ringing. Yeah, so why is there a difference between the two? Well, basically every ECU comes online at that point. So every ECU has to announce and acknowledge that they have received that message. In doing so, obviously, if there was a problem, in this case, we know what the issue is. There was a breakdown in the connection between the network. Everything from one side of the network was suddenly trying to send a message back through a poor connection, and creating that ringing effect. So this is where we have suddenly duplication of that ripple on the acknowledgement spike, when actually most of the rest of the packet doesn't receive that. Yeah, so there was a bit of a key indicator there for us as well that we actually hadn't already, like I said, that we may have overlooked initially. The other thing to notice here as well is the acknowledgement spike itself. Now, something that I think in the original case study we looked at, you could see there was quite some spiking on the acknowledgement part of that. Now, it's not a problem. However, it's good to understand why that's happening. So why is this voltage during the acknowledgement spike so high? I mean, in this instance, we're up to nearly 4 volts. Yeah. Now, traditionally with CAN high, we'd expect 3.5 volts. So it's stepped over that mark by 0.5 volt. Now, why is that? There is a terrific series on YouTube from a gentleman called Joe Bell. I do encourage people to go review this because I've learned a lot from these videos. He actually explains what's going on here and demonstrates how it's happening as well. So basically, as every ECU comes online, acknowledges that message, it's changing the resistance value of the network momentarily. And in doing so, forces actually the voltage to creep up ever so slightly. In this case, 0.5 volt. So this is useful information as well, because this can tell you whether or not you have a number of ECUs online. The more ECUs you have, the higher that acknowledgement spike is going to be. The less ECUs, the closer it's going to be to actually where the data was being sent at around about our 3.5 volt mark. So there is some diagnostic value within this section here. Please don't assume that it is a fault when it's likely it isn't. So if we skip forward a little bit more, again, you can start to see the differences between the data here. This was obviously where it had shifted. I just want to focus again here just on can high and can low near the front body control module. So again, we can take the Pico zoom tool and zoom in. You can already see the shift between can high and can low. Yeah, there is a difference. They should be at the same point. And what we believe is happening here is actually the connection to can high is ever so slightly off at this point. Yeah, there's something wrong with that. Okay. And then finally, as we keep going through, you can start to see how bad it gets. You know, there's clearly disturbances. There's clearly issues between the two ends of the network, and obviously it was due to that connector. Okay, so I hope that helps. It's a bit of a review of a previous post, and obviously looks at some slightly different information that we may have not seen, but again, hindsight's a wonderful thing, and there is always something to learn, and I think this is why I personally love this industry. It's never a dull moment, and there's always something new to learn every day. So thanks for watching, and see you next time.
Hopefully that gives you a nice little understanding there in terms of CAN communications and how we apply PicoScope to that. Cam and crank synchronization, another one. And there are loads and loads of other case studies if you go on the website or increasingly now on our YouTube channel. So we're just going to recap, coming to the end. Hopefully this has given you a nice understanding of PicoScope and where you could apply it to everyday use. We're just going to run through understanding waveforms, and Phil's got one final little trick to show you. So just recapping, available help, those guided tests, absolute gold. They're going to show you how you connect to the component. They're going to build your understanding of what a waveform is for the component you're testing and what to look out for when things go wrong. They'll give you guidance about, you know, where faults might be, and also how that component interacts with other components within the vehicle. So a huge amount of information there in the guided tests. And most importantly, particularly from a new user point of view, having that understanding of where you go and find the component and capturing the data, really, really key. Then we've got our waveform library, and we haven't done much on this yet. So effectively, we've now got 8,000 guided, waveforms in the waveform library now, Phil? 7,000. Sorry, 7,000. Yeah, so we're thousands of waveforms. Effectively, you can go on there. So the waveform library, you can look by vehicle make, by model, by engine code. You do have to have PicoScope connected to use the waveform library, and Phil's going to actually show you live on there in a moment. So you do have to be connected. Clearly, you have to have an internet connection, and you have to have a login from the forum. So the forum login, so the username and password for the forum is what we use for the waveform library, and it allows you to connect. Also allows us to know who's uploading any waveforms. So if we spot something we want to ask questions about, we can come and find you. And effectively, you can use all of these guided tests, so over 7,000 tests now. You can download them, you can open them up, and you can run the same test on your vehicle, and you can compare. And it's that comparative from a known good waveform against a vehicle that you're trying to diagnose that is hugely valuable to you as a technician. So is that capture waveform and compare. There it is, that's what we see. So we log in and we've got all of those different pull downs that we can look at to find our vehicle, and we can have even if you're lucky enough to have an 8-channel scope, you can have 8 channels of data that you can download, either the whole set of waveforms, or if you're only interested in, say, cam and crank, you can just download the ones that you want. Right. Phil, I'll pass pass you over to Phil now, and he's going to take you through looking at the waveform library and show you how to log in and how to download a waveform. Thanks, Phil.
Thanks, John, for that. So what we're going to do is we're going to look at my screen on my laptop and just run through some things because we've got some new bits to show you. So first, most important bit is please keep your version of PicoScope 7 updated, because if you've got one of the first releases, you will not see Waveform Library logos in there. So we're going to look at the where to find it, how to pin it, and what it looks like. So we're now going to go over to my laptop, and I have actually pinned my Waveform logo on my screen. So if I go to more, you will see that there is a nice little star here, which has actually got a nice blue logo. So I've pinned that, so that is always there and ready for me to use. Now, with the latest version of software, we also have a very nice little toolbox logo at the bottom of our screen. So what I'm now going to do is I'm going to go on to, I've logged in, so I've got my automotive scope connected, internet connection, and I've logged on to my account, and I'm now going to go and look for something. So remember that on the screen we have our drop down, pull down menu. So we're going to pick Audi, and then for me to go to make, I do that. And remember that the little slide bar is on the is in a different position now than it used to be. So we're going to pull down and see what we can find, and we're going to go down to this Q5, and we're then going to go search. So we're going to see what we can find, and on here we've got all of the different waveforms that we've got, so we can look and see exactly what there is. So here we've got all the information on the screen. So let's actually look at this one. So what we're going to do is we're going to hit the button, and that is going to download it onto my screen in a minute. Okay, so here we can see all of the information that we've got. So what we've actually got here is we've got camshaft sensors and crankshaft sensors, and on this particular vehicle it's got 2 camshaft sensors. So we're looking. So what we can also do here is actually look at the vehicle details, and it will show you all the vehicle details. So you've got Audi Q5, the year, transmission, the engine code, what it was, what was happening. So this is really, really important. Not forgetting that we can move any of the waveforms around the screen. So you'll see there that I've just dragged that one down and dragged that up. So I can then look at any of the bits on here. So key features, one is always save your waveform, put as much information on the waveform as you possibly can, because in 12 months time when you go back to that you're going to forget totally what you did. Also, not only can you put the sensor type, but you can also put terminal connections, and you can put that in the notes section, and the colour of the wires, so that if you do that particular make a lot, you've got all that information built into your waveform. And again, it is such a powerful tool to look at the waveforms, save them, look. And one of the most basic questions that we normally get is, how do I know whether it's a good sensor? Look on the waveform library. Look to see how different Hall effect signals can be. And like everything, even between models, they'll change. So always look and save whatever you've got, put the information on the screen, and you can also then start to understand what each waveform looks like and have a better understanding. But anyway, that's just a small introductory to the waveform library. So just remember, you've got to have Pico 7 or Pico 6, it's got to be automotive, you've got to have an automotive scope connected, and you've got to have internet connection. And if you then want to, you just go on and join up on the forum group with an email and a password, and then you can access any of the 7,000 odd waveforms on there already. So anyway, we're going to go back to John now.
Thanks, Phil. So, yeah, waveform library, really, really powerful and increasing in waveforms every single day. Okay, just one final little animation, which I think just shows you again the diagnostic process. And I don't think you'll really need me to say too much, but we'll just take an example here. So we've got a wheel speed sensor in this case, so we're going to take our vehicle on a road test and we're going to capture our data. Now this technician, the same as you, is not going to know when you capture that waveform for the first time. Is it good or is it bad? So again, we're back to where can we find helpful, useful information and data? Well, of course, so we're back to our guided tests. So particularly looking at waveform notes. We can also look, as Phil's just talked about, in the waveform library. And like I said, a good known waveform from the waveform library is absolutely key. So we're going to search by vehicle. I say we, our technician is searching by vehicle make, by model. We can put a year in, and then he can scroll down. He's been lucky, he's found exactly the waveform he wants straight away. There we go. Similar to the one we've connected. What else can we check? Technical data, really, really valuable. Is there a known fault with the vehicle you're working on? You know, always check that. So we're going back, and he's been lucky here. We found a service bulletin which shows and highlights exactly the problem that we're seeing. So there's our faulty component and our wheel speed sensor. And look, it's got the same issue as we've seen in our waveform. So technician replaces our component and back onto the vehicle. And like we've said a number of times now, final job for any PicoScope technician, retest the component when it's on the vehicle. It's not beyond possibility that you get a faulty component straight out of the box. So there we've got our nice square edge wheel sensor waveform, and we know that the fix is absolutely complete. So that's understanding waveforms. Right, so we just got last few bits to finish up. I hope you've enjoyed our introductory session to PicoScope oscilloscope diagnostics today. This is really just to dip the toe in the water in terms of working with PicoScope. There's lots more to come. We're doing more videos in this series, so there's going to be a whole video on looking at electric vehicle testing. We're going to do a session on working with pressure, so WPS, and also looking to do an MVH one also. So look out for them and keep in touch with your distributor, who will keep you informed as we do more sessions. Some final things to finish on. Essential links. So I've mentioned it earlier, please do download our automotive app, available on Google Play and on the App Store. So it's a really good way, particularly as a new user, to download it, and it takes you through the basics of working with PicoScope. A lot of what we've covered today is in there. We've got some short videos. We show you a lot more animations. There's a lot more case studies in there that show you how PicoScope fits in your everyday diagnosis. It's just giving you a show through on the app. Lots on the video. So we have obviously videos on our website, so www.picoauto.com, as well as on our YouTube channel, which is Pico Automotive. On the bottom of this video, we will send you a load of links so you know where to go to. Also our automotive forum, so go on there, have a look at those one waveform, one pictures. Loads of questions and answers on there, which will really help you get going with PicoScope. And there's a whole list of essential links. They are in the bottom of the video as well. So I'll just run them out there. Okay. So thank you for joining us. And thanks to Phil for helping us go through PicoScope on vehicle. And like I said, more to come in the future. But for now, thank you for listening and all the best on your PicoScope diagnostic journey.